Okay, g'day students. Welcome to our final lesson on sequencing. And today we're going to look at applications of geometric sequences. So the point of today's lesson is that you should be able to use geometric sequences to model and analyse practical problems involving geometric growth and decay. We're going to analyse a compound interest loan. We're going to look at the decreasing height of a bouncy ball. And we'll look at depreciation using declining or reducing balance method to depreciate as well. So let's have a look at our first application. So the first one is a bounce height application. So for example, we have a ball bounces repeatedly reaching 70% of its previous height each time. Now if the first bounce is 3 meters, how high will the fourth bounce be? So let's visualize what we have. We've got a ball that bounces. First bounce, so term 1 is 3 meters. We don't know term 2, 3 or 4 yet, but we know the height of term 1 is 3 meters. So all we need to do now is just identify and apply. So we know term 1. So where's our term 1? Here it is. We know our ratio 70%, so 0.7, and the term number is going to be 4. So all we're going to do is substitute into our geometric sequence formula. So the nth bounce, or the fourth term, is going to be the first term multiplied by the ratio to the power of n minus 1. So once we found that, we can just substitute and solve. And we can just say, well, on the fourth bounce, the maximum height of the ball will be 1.029 meters. Now our second example of what are we looking at, geometric sequencing, is that of compound interest. And so compound interest involves interest on interest. It's calculated as a percentage on the total funds. So the customer receives interest at the end of each time interval. So if we have a look at our geometrical interest formula, we're going to think of a few terms. We're going to have a look here and we'll say, where is my pen working? Yep, there it is. This is one with the amount at the end of a certain period is the original amount, 1 plus the interest rate to the power of n. Now we're going to look at that interest rate as a decimal, and from that interest rate we can get our common ratio, and we can call it a growth factor. Now to get that growth factor, we're just going to say 1 plus that interest rate. So if it's 5%, it's just going to be 1 plus 0.05, for example, so would then equal 1.05 for your growth factor, for example, in this one here. And then we can also summarize this at the total amount equals the original value at 0 time multiplied by the ratio, the common ratio to the power of n. You can see that because I've got a 0 here and a 1 here, I've said n minus 1, whereas I've just said n here. So you can see that that's it just summarizes that equation and makes it a little bit smaller. Now it is appropriate because we're working with time and we start at a 0 time. Instead of using T1, we're going to use A for an amount and then a 0 for starting at 0 time. And so if we have a look at compound interest in this table here, you can see term 1, the amount is $100. 5% of 100 is $5. So this here, the interest earned, well, that's just going to be added onto the 0 term. So we're just going to say the amount at the end of the first year is $105. Now, if we look at compound interest, remember it's interest on interest. So we need to calculate 5%, or our growth rate here, a growth factor or a common ratio is still 5%, and 5% of 105 is $5.25, and we just add that on. and you can see that that increases a little bit more each time. Now we can express that according to the geometric sequence formula. So the amount at the end of 5 years is just going to be the amount you started with, the original amount, 1 plus the interest rate. So remember, that's your growth factor, 1 plus I to the power of n, which is the number of time periods. And that should end up the same amount as that. So let's have a look at an example. So we want to determine the amount, the account balance at the end of the term for the following investment. So we've got a deposit of 15 grand, interest rate of 4.6 compounding annually, and a term of 8 years. So we've got our appropriate formula here, and we can just substitute into that. So let's figure out what we know. So first number is this, 15,000. That looks like an original amount. The next one is an interest rate. So this looks like an I. We can combine that to make R. We add that to 1 to make an R, so that's fine. And then we've got a term of 8 years. So that's the number of time periods. So we just sub that into our formula now. So the original amount, which is 15 grand, 1 plus 4.6%. So you can see that 4.6% equals the same as 4.6 over 100, or divided by 100. So you can just move that decimal a couple of places. And then that's to the power of 8 because we have 8 time periods. So we just substitute that into our formula, and the account balance at the end of this time period is $21,495. If we change the compounding period, so if we change this, instead of saying annually, and we can say, oh, let's make it monthly, we're going to change the interest rate, and we're going to change the time periods. So what do we change? We change this. That's going to be a factor of 12 less because it's monthly, so we just divide that by 12, but we multiply this by 12 because it's monthly. Now when you're doing this on your calculator, don't round off. Keep this in your calculator and just spit out the final number, then you won't get any rounding errors, and that's important, particularly come assessment time, because if you're a cent or two off, you can be marked incorrect for that. Now, declining or reducing balance, I've also heard it called diminishing balance, is another form of depreciation. And this is based as a percentage of the previous year's value. So it's a declining or a decaying, so it's geometric decay in this case. And instead of an R being more than 1, that's going to be less than 1. So let's have a look here. So we've got our value after n number of years equals the original value multiplied by 1 minus that reduction factor, or that interest rate, sorry. So 1 minus that interest rate will be the reduction factor. So that's R, or the common ratio, and that's going to be to the power of n. Now, we can summarize that as saying the original value at 0 time equals the value and the nth year times R to the power of n. And that should be 0. Oh no, that's right. And R should equal 1 minus I. And you'll get a curvy graph, of course, rather than a flat graph. Now, if we want to determine the value of a depreciated item, let's have an example of this. So a phone bought for $1,800, depreciated with a reducing balance rate of 12.5% after 3 years. So all we need to do is identify the appropriate formula and substitute in, which is really nice. So we've got our original amount, and then we've got an interest rate, and then we've got the number of years. There we go. And then we just sub that into the formula, and will spit out the answer, and the value of that phone then is $1,205.86 after 3 years. So pretty quick one today. We've used geometric sequences to model and analyse some practical problems. Now we've looked at geometric growth, in particular compound interest, and then you'll have some homework regarding the bacterial population. We've also looked at geometric decay using the bounce of the ball and reducing balance depreciation. There's a fair bit of homework for you to work through on your mastery lessons. That's important to give you a good breadth of understanding. Once you've done that, can I please get you to work on, and I'll just look at the right number, that's actually page 174.